Hi, everybody. Um, Nice of all y'all to be here. Today, we'll be talking to you and introducing an app that we've recently released. Otto is an open source, web-based, automated ETL workflow manager that orchestrates the gathering, transforming, and loading of data at scheduled intervals. My name is Matt. I'm here with Jing, Joe, and Katherine. First, we'll introduce workflows in ETL. Then we'll talk about existing solutions and where Otto fits into that ecosystem. After that, we'll talk a little bit about how to use Otto. And finally, we'll talk about the journey we took in developing Otto. To start us off, we'll talk about what it means when we call something a workflow. A workflow is a series of tasks executed in sequence from the beginning to the end of a working process. A person's morning routine is an example of a workflow. I wake up, I drink a cup of water, I brush my teeth, I put my contacts in, and that's the end of it. There are a myriad of things that might start or initiate a workflow. I may be responsible to check for any updates to some database at noon each day, for instance. Or perhaps I receive an email from my manager requesting that I handle a bug that they found in the app. Alternatively, I might get hungry, prompting me to start my lunchtime routine. From there, a workflow has actions that are taken to achieve the desired goal of the workflow. If I find new data, I might pull that data from the database to update our records elsewhere, or after writing a fix to a branch, I might push that branch to GitHub. To deal with my hunger, I might drive to a local restaurant and grab a bite to eat. Some of these workflows require manual input from me. I need to debug the application myself, for example, but others could potentially be automated. Workflow automation removes the need for manual input to run workflows. Workflow automation is conducted by what we call a workflow orchestration engine. Workflow orchestration, as we define it, is the act of scheduling, executing, and monitoring tasks in a workflow to achieve a specific business objective. A workflow orchestration engine is responsible for initiating a workflow and executing the individual tasks that make up that workflow. A workflow orchestration engine handles the sequencing and execution of each node. It also handles the transfer of data between nodes. For instance, if a workflow is initiated by an incoming email, there may be information in that email that needs to be used in the next phase of the workflow. The workflow orchestration engine handles the transfer of data from one node or task to another. Finally, a good workflow orchestration engine logs data in the workflow executions. When an automated workflow execution fails, you want to know it failed, and you want to know why it failed. Otherwise, failed tasks go uncompleted and no fixes can be made to ensure future tasks are properly completed. There are many different types of workflows, but today we'll focus on one particular type, the extract, transform, and load data pipeline. Extract, transform, and load, or ETL for short, is a data pipeline process of combining data from multiple sources into a central repository. Businesses may have dozens of different transaction processing systems powering the customer-facing website, planning routes for vehicles, managing suppliers, etc. Since these systems are often critical to the operation of the business, they are usually expected to be highly available and to process transactions with low latency. The administrators for these databases are therefore reluctant to let business analysts run ad hoc analytical queries on them, as those analytic queries are often expensive, scanning large portions of the data set. Furthermore, if relevant data is scattered amongst multiple databases, it has to first be gathered from those databases and placed in a holding location to be analyzed as a unit. The solution to these problems is to coalesce all that data into a central database that is optimized for analytics queries. The process of pulling that data from multiple databases, transforming it, and loading that data into a central database is what we call ETL. Now, ETL has three distinct steps. Data extraction is the step where data is retrieved from disparate sources, such as databases, APIs, or web services. Data transformation involves converting the extracted data into a consistent format that is compatible with the destination system. The final step is data loading, which involves placing the transformed data into the target database or other data storage application. An optional validation step may also be added to make sure that the load operation was performed successfully and accurately. Now, ETL can be further divided into modern ETL and light ETL. The difference between the two is a matter of scale. Modern ETL may involve the extraction of data from a plethora of data sources. The workflows extract and transform terabytes or more of data at a time from these sources. Finally, the data is loaded into data warehouses or data lakes. These are repositories designed to handle large amounts of data. By comparison, light ETL involves significantly fewer data sources. The data pulled and transformed from those sources is measured in megabytes. Similarly, the final destination for the data is often smaller databases or applications like Google Sheets. Now that we've talked about that, let's see a more concrete example of what a light ETL workflow looks like. A pharmaceutical company named Pharmaco might have an ETL workflow that looks something like what you see before you. In this case, Pharmaco is attempting to decide which drug manufacturers to work with. To do this, Pharmaco is pulling FDA inspections and citations data on the various companies and matching them up with Pharmaco's existing information. The workflow starts with the extraction of data from 4 distinct sources. 2 involve making HTTP requests to the FDA API to get information on their inspection and citation records. The other 2 extractions are from an internal company database where Pharmaco stores information on their product catalog and any complaints that were registered for those products. The next step is where the data is transformed into a format that's useful for future analytics. First, the FDA inspections data is combined with the associated FDA citations data and gathered from the FDA API. Then that transformed FDA data is combined with the extracted Pharmaco product catalog and complaint data. Finally, all that combined data is loaded into a database that the analysts are free to work with. And altogether, that completes the ETL pipeline. Now, Jing is going to take over from here, and it will talk to you about existing workflow automation tools.
Thank you, Matt. Now let's take a look at what problem Otto solves. Companies or users who need to automate their workflows can choose between building an automation tool from scratch or using existing solutions like Otto. So why would a company use existing solutions instead of making it from scratch? Well, making it from scratch requires significant investment upfront, unless workflow automation is your company's core competency, or maybe you need a ton of customizations that none of the existing solutions offer, then using an existing solution would make more sense. Now let's look into what are the existing workflow automation tools and what Otto has to offer. So existing automation tools targets different types of users. Some apps like Zapier doesn't require any coding background. At each step of the workflow, the user can choose from a list of actions, and these actions are written in plain English. For example, if an email is received, then send a notification to Slack. This type of apps generally have very intuitive UI and anybody can use it. However, they are usually less flexible for data manipulation, and they can't handle complicated workflows or large amount of data. For example, they may have limitations on how many branches you can have or how much data you can process. At the end of the spectrum are code-based solutions like Dexter. This type of apps targets more technical users. You can't use it if you don't know how to code. They're usually very flexible with data manipulation. Dexter, for example, allows users to use their local IDE to write data processing code. And they can usually handle complicated workflows with large amount of data. However, they are generally more difficult to set up and have steeper learning curve, especially for non-technical or semi-technical users. So Otto comes somewhere in between. Our user needs to know how to write code to interact with their database and transform their data, but we have an easy installation process and intuitive UI. We can support branching of workflows, but we have limitations on the amount of data we can handle. We can support up to 255 megabytes of data per workflow. For farmer code, this translates to about 200,000 rows in the 15-column relational database table, which is more than enough for their workflows. Now, let's look at some other features that existing solutions offer. Most existing workflow automation apps offers a lot of integrations. NAN, for example, offers integration with more than 250 apps, including social media and messaging apps like Facebook and Slack. They also offer different types of workflow triggers, such as webhooks, scheduling, and manual triggers. For an ETL user, however, it can be unnecessary and might make it difficult to navigate and find what you really need. There are ETL-focused solutions as well, such as Dexter and Talent. However, they can be lacking in terms of observability, and they generally support Python for data transformation instead of JavaScript. So here comes Otto. We are an open source ETL-focused workflow automation tool. We don't provide a ton of integrations like the other existing solutions, but we do provide Postgres and MongoDB integration, which are more relevant to ETL users. We allow users to use JavaScript to manipulate their data, and we provide high observability into nodes and workflow executions. Otto is a nice option for light ETL users who prefer to use JavaScript and want high observability for their workflows. So now let's move on how to use Otto. Our app is Dockerized, so a user just need to download the Docker Compose YAML file from our repository, run Docker Compose up, and go to your browser and enter localhost 3001. This will bring you to our workflows page where you can view existing workflows and create new ones by clicking the Create Workflow button, and then you enter your workflow name and the workflow will be created. Once a workflow is created, our user will be redirected to our Edit Workflow page where they can start creating their workflows. We can start by clicking the Create Node button to add nodes. We have 4 types of nodes here: schedule, extract, transform, and load. For extract, we have 3 subtypes: API, Postgres, and MongoDB. I'll briefly go through what each type of node does, and for extract node, I will use extract API as an example. So the schedule node takes workflow start time and execution frequency as input. Once a workflow is set to active, it will be automatically executed by a cron job according to the schedule. The extract API node initiates HTTP requests to API endpoints. It takes URL, HTTP verb, and optional header, body, authentication data as input, send the HTTP request, and save the returned data as an output. The transform node executes user JavaScript code against previous node's output data and save the returned data into the database. The load node takes client database connection information and user SQL code as input. When executed, it connects to the client database first and then execute the client SQL code to update or insert into the client database using the data from the previous node. We allow the user to set both staging load database and production load database. When a workflow is inactive, we use the staging database. And when a workflow is activated, we automatically switch to the production database. Once we created our nodes, we can connect them by clicking and dragging between the little dots on the nodes. These connections are called edges. The nodes that are connected to the left dot at the node's input, and a node cannot be executed unless all the input nodes' executions are successfully finished. The little green tick on the node indicates the execution status of a node. If an execution fails, it will show a red cross instead, and if a node hasn't been executed yet, then it will have nothing on it. Let's look at this transform node that hasn't been executed. As you can see, 3 nodes lead into this transform node. And if we click into the transform node, a modal will open. On the left side of the modal are the 3 input sources for this node. Each input source data is presented on a different tab. Since this is a transform node, the user needs to enter JavaScript code to transform this input data. And once the code is written, the user can click on the Save and Execute button. This will save the user code into our database, execute the user code against the input data, and then save and display the output to the left. Now we can continue this process until we complete our workflow. Once our workflow is completed, we can execute the entire workflow by clicking the Execute Workflow button, in which case all the nodes will be executed in order according to their dependencies. For example, inspections transform won't execute until the inspections and citations are both finished. Independent branches will be executed in parallel. For example, client local Postgres and client remote Mongo can be running at the same time. If the workflow is tested and runs properly, then we can set it to active. Once activated, it will be executed by a cron job according to the schedule. On the left sidebar are our execution logs, where we track workflow executions for both test and active workflows. If we click into one of the logs, we will be able to see the workflow at the time of execution and the execution results. We can also view the metrics of a workflow by clicking the Active Metrics button. We track nodes and workflow execution metrics for the most recent version of the active workflow. We will go into more details about logs and metrics later, and now I'll pass it on to Joe, who will start talking about how we develop Otto.
Thanks, Jing. Over the next few slides, I'm going to give a general overview of Otto's architecture. Otto uses a 3-tier architecture, and as the name implies, is divided into 3 separate layers: the presentation, application logic, and data storage layers. Each layer is responsible for its own set of associated functionalities. The presentation layer is responsible for displaying the user interface, presenting information, receiving user inputs, and handling user interactions. The presentation layer is built using React. The application logic layer contains the business logic and core functionality of the application. Some responsibilities include processing user inputs from the client, transforming extracted data, and managing the flow of information between the client and the database. This layer is also responsible for extracting data from API endpoints or databases and loading transform data into our target database. Our application logic is implemented using the Express framework. Finally, the data storage layer is responsible for managing the storage of workflow and metric data. Otto uses Postgres for its storage needs. Now that we reviewed the overall architecture, I'd like to delve deeper into Otto's client-side functionality. More specifically, I'd like to discuss how we implemented one of Otto's most critical components, the interactive node-based UI. During the course of this section, I will also highlight some of the difficulties and trade-offs we encountered along the way. But before I dig into the details, let me first describe the characteristics of a node-based UI. A node-based UI allows users to create, manipulate, and interact with nodes to perform various tasks. Here's an example of a simple UI that contains 4 nodes. In addition to creating nodes, node-based UIs allow users to connect nodes together by drawing lines between them. As Jing previously mentioned, these connections are referred to as edges, and they define how data flows from one node to another. Beyond the most basic functionality, we had a few additional ETL-specific requirements that a node-based UI needed to provide. These requirements included creating and modifying custom schedule, extract, transform, and load nodes, storing associated and specific ETL metadata within each individual node, storing associated output data within extract, transform, and load nodes. For example, an extract node should store the data retrieved from an API endpoint within a self-contained output property. And lastly, connecting schedule, extract, transform, and load nodes to define a complete ETL workflow. After defining our requirements, we needed to decide whether to build a node-based UI from scratch or to integrate an open source library. But before we can make this decision, we needed to consider the technical challenges associated with building such a node-based UI. We identified 3 significant challenges. The first was rendering performance. Rendering a large number of nodes and connections in real time could impact performance. The second was state management. Keeping track of the state of the node-based UI, including the positions, properties, and connections of the nodes, would require a robust state management system. The third was drag and drop interactions. Implementing responsive drag and drop interactions for nodes would require handling mouse and touch events, calculating positions, and updating edges in real time. Despite the challenges, we also identified 2 significant benefits to building a node-based UI from scratch. The first benefit was the ability to create a tailored solution that could perfectly fit our application's specific requirements. The second benefit was avoiding bloat and not having to worry about integrating a library's code that was non-essential or that would only be partially used by Otto. After weighing the challenges and benefits of building a node-based UI from scratch, we ultimately chose to use a library called React Flow. React Flow is a React library that's specifically designed to help build interactive node-based user interfaces where users can create, manipulate, and connect nodes to represent workflows. There are three main reasons why we chose React Flow. First, React Flow came with many of the features we needed out of the box, like dragging nodes, adding and removing edges, and zooming and panning. Second, React Flow addressed the previously mentioned technical challenges associated with building a node-based UI from scratch. It optimized rendering performance by leveraging React's virtual DOM, internally tracked the nodes and edges state, and abstracted away the complexities of tracking mouse events and positioning. Lastly, using React Flow would allow us to focus on implementing the unique and valuable aspects of our application rather than spending time on the mechanics of a node-based UI. Despite its many benefits, React Flow was not without its trade-offs. The biggest trade-off was that the tool enforced a fairly rigid structure for nodes and edges. First, multiple nodes or edges were required to be organized as arrays of objects to be consumed by React Flow. Second, individual nodes needed to adhere to a specific structure. For example, each individual node was required to define a unique ID, a position, and a label. Additionally, if we wanted to define any app-dependent data for a particular node, we would need to store the data within a node's data property. These restrictions would have implications on how we stored the node and edges data in our database. Next, I'd like to spend a few minutes exploring how we approach storing Otto's application data. One of our most significant infrastructure decisions involved determining how our data would be stored, as well as the type of database in which our data would be stored. However, before we could make an informed decision, we needed to identify Otto's data storage and querying requirements. We identified 4 critical requirements of Otto's database. First, we needed a way to represent Otto's entities and maintain any relationships between them. Otto's entities include node, edge, workflow, execution, and metric. Examples of relationships include the one-to-many relationship between workflow and node, and the one-to-many relationship between workflow and execution. Our second requirement was the ability to efficiently store node data that may vary in shape and structure. As an example, the schedule and load nodes both define a data property, but the schedule node's data property contains 3 properties, while the load node's data property contains 8 properties. Our third requirement was the ability to easily query node and edges data so that the data could then be formatted into arrays of objects to be consumed by React Flow. The fourth requirement was the capability to efficiently store workflow data that may total up to 255 megabytes. Taking our database requirements into account, we identified 2 database types that might be capable of meeting our database needs: relational and document. More specifically, we considered the Postgres and MongoDB databases. But before we can make a final selection, we needed to determine how well each database type fared against our pre-established database requirements. The entity relationship diagram currently on the screen represents the first option we considered and depicts the structure of Otto's entities when using the relational model of data. Let's see how well option 1 meets Otto's database requirements. It meets the first requirement because it represents all of our entities and maintains the relationships between them. It fails the second requirement, however, because the relational model would not be an efficient method of storing unstructured node data. Relational databases impose a rigid and predefined schema, and as a result, there would be a substantial number of unused columns in the node table. It also doesn't meet the third requirement because querying node and edge data would require multiple joins to return all the nodes and edges associated with a single workflow, and this would be suboptimal. It does, however, fulfill the final requirement. Since each entity is allocated a dedicated table, a relational database will have no trouble handling auto storage needs. Next, this slide visualizes database option 2 and depicts the structure of Otto's entities within a document database. In this version, a single workflow document stores its own data, as well as the data for node, edge, metric, and execution entities. This option meets the first 3 requirements, but fails to meet the fourth requirement. Let's take a look at each one. First, all of Otto's entities are represented and nested within a single document. Second, this option can support variable node structure. After all, document databases excel at storing unstructured data. Third, it would be easy to query node and edge data because a single workflow query would return all the data we needed. The only downside of this option is that each individual MongoDB document cannot exceed a maximum size of 16 megabytes. This means that all entities, most notably the node entity, would compete for a limited amount of storage space within the workflow document. This limitation would be untenable. At this point in our database analysis, it was clear that options 1 and 2 met many of our requirements, but not all of them. Despite their benefits, each option possessed at least one glaring downside. As a result, we considered a third option, and in doing so, returned to the relational model of data. In this final option, Otto's entities would look something like this. Like the first option, the workflow entity shares a one-to-many relationship with execution and a one-to-one relationship with metric. However, unlike the first option, the node and edge entities are now attributes of the workflow entity, and each of these two columns are assigned a JSON-B data type. This option fulfills all of our requirements with one caveat. First, it represents and maintains the relationships between Otto's entities. Second, by using JSON-B columns, a single workflow row stores associated nodes and efficiently supports variable node structure. Third, it's easy to query nodes and edges data for use by React Flow, and it handles Otto's workflow storage needs. The only downside to this option is that accessing an individual node requires iterating over all of the nodes that are stored in the node JSON-B column. As a result, I've added an asterisk next to the requirement number 3's checkmark. Of our options, we felt option 3 best met our database requirements and with the fewest trade-offs. As a result, we selected this option. Now I'm going to pass it off to Katherine to discuss Otto's server-side functionality.
Great, thank you. First of all, I just want to mention that if my voice is a bit hoarse, I'm sick, so apologies for that. As we mentioned, Otto supports branching workflows, by which we mean multiple inputs can feed into other nodes, as in this diagram here. For instance, a user might want to extract data from 3 separate APIs, combine that data, and then use that merged data in another transformation. And like you see here, the transform node uses data from the extract1 and extract2 nodes. However, this kind of branching workflow does present some challenges in implementation. As we mentioned here, the transform node cannot run before extract1 and extract2 are done. Otherwise, it does not have the data that it needs to do its transformation. However, if we have extract1 and extract2 finished, then there is really no reason why transform1 shouldn't start automatically. Otherwise, that creates unnecessary bottlenecks and slows the workflow down when the point of a branching workflow is that things can happen concurrently. So this was an implementation challenge we faced, and here is a diagram of the algorithm we use. There's a lot here, so we will break it down in the next couple of slides, but at a high level, it's a recursive algorithm that serves 2 purposes. First, it traverses the graph of nodes and edges to find which nodes are dependent on others. And once it has that structure, it will handle the order of node execution so that nodes will only execute when all their dependencies are complete, but that they also will not wait for that, or rather wait when they don't have to. And the way we did this was using JavaScript's built-in asynchronous code execution feature known as promises. And here's how it works. So we first call the algorithm on node at the end of a complete workflow, which will always be a load node. And when we call this algorithm on any node, it will look up any edges whose target is that node. So in the diagram here, whatever is on the right. And from that edge, it will get the nodes incoming, which here appear on the left. It will add those nodes to an array, and that array will be passed to and wrapped inside a JavaScript promise. And inside that promise, the function will recursively call itself on each of those incoming nodes. And whatever the current node of the call is will defer its execution until all of its dependencies are complete. And so, as you can see, it thus progresses toward the beginning of the workflow, creating promises at every step of the way, until it reaches the end, which is always a schedule node. And the schedule node will resolve immediately. It will never have any incoming nodes. And once it resolves, any of the attached nodes can now begin. Here, extract 1, 2, and 3. And transform 1 will wait for 1 and 2 to complete until it itself executes. And similarly, transform 2 will wait for extract 1 and 3 to finish and will not execute until those are done, but it will happen concurrently. One thing that we do want to note here is that transform 1 and transform 2 both depend on extract 1. In order to prevent us from having a situation where we execute extract 1 twice here, which would definitely not be what somebody wants and would possibly cause issues down the line. We keep track of or memoize the promise object that we create. And we reference this in all subsequent promises, ensuring that no matter how many nodes are waiting for any given node to finish, there's only one execution of it. And in an ideal world, this is what will happen. Like everything will go without a hitch. But we live in the real world, and in the real world, errors happen. And so when we designed Otto, one thing that we really wanted to emphasize was robust observability into these errors so users can troubleshoot. And specifically, we wanted to distinguish between two types of errors because they should be treated differently. For instance, there are some errors that originate inside an Otto workflow. For instance, a user might make a syntax error or a typo inside some JavaScript code that they wrote. That's called an internal error inside Otto. And perhaps, however, there's an error that originates outside Otto. For instance, we might be trying to extract from an API that is temporarily down. We call these external errors. Regardless of which type of error happens, however, Otto will catch this and provide detailed, easy to understand information about that error on the node at which it occurred, including interpretations of any error codes, which can also be opaque. And when you are reviewing workflows, you can see what exactly happened. And additionally, for external errors, Otto will also automatically retry execution after increasing intervals of time. Because if you have an API that's down for like 5 seconds, then you probably don't want to shut down execution for an entire day or week or whatever interval you've got, just because you happen to try to execute it at the exact second that the API didn't work. But if you wrote a syntax error in your code, then no matter how many times you retry it, that syntax error is still going to be there. And so there's really no point retrying in that case. And here you just see a very brief flowchart of how it works behind the scenes on the back end. As you can see, there's many different points in which an error could occur, and Otto will try to catch it at any of these points and handle it then. And closely related to errors is logging. So Otto gives users many tools to view the history of their workflow executions. So whenever a complete workflow is run, a log will appear in a pane next to the workflow layout panel, and this is what that pane looks like. As you can see, every log contains some details such as the timestamp of when it ran, whether it succeeded or failed, and whether the execution was a test or whether it occurred live on the production database. Regardless of whether it's a test or an active execution, active meaning live, if you click that log, then Otto will show the workflow layout screen as it looked at the time the workflow was run. And if you click on any of the nodes at that point, you can see exactly what input data was passed, what was sent as output, any errors that might have happened, and so on. That way, you don't have a situation, for instance, when a workflow failed at midnight last night, you don't know why. You can see exactly what happened. And the way we do this is with server-sent events, because these logs will all update in real time. So this is a diagram below of how that would happen. Essentially, the server creates an event at the time any node completes or any complete workflow is done. And the client will listen for such events. Every time it notes one, the display will update automatically to reflect what happens. So for instance, in the workflow layout pane, that's when the checks or X's or whatnot will appear, and the input data will appear on either side of the modal. And we store logs in a database as well. This is just the internal schema of it. It should be pretty self-explanatory. It is relational to workflows in a one-to-many fashion. Each workflow, of course, can be executed an indeterminate amount of times. One thing we do want to note here is that we store the workflow state, again, as in JSONB format. This way, we can render the workflow layout exactly the way we would a live current layout. And so closely related to logging are metrics, and Otto tracks several kinds of metrics about workflow execution to allow users to further fine-tune them. And we track two types of metrics. One is at the workflow level for the entire workflow, such as the number of successful executions, percentage of executions that were successful, and how long the entire workflow took to complete. For instance, if a user notices a workflow is unusually slow, they can go investigate. And we also track metrics at the node level, including how long a given node took to execute, which is useful to identify bottlenecks, like code that might be super slow that you can improve. We have how often any given node failed, which can identify problematic code or APIs that are not super reliable. And finally, we track how much data on average every node processes, which is useful sometimes for data analysis purposes. And we do this just by measuring the size of the stringified JSON, since everything is represented in JSON for input and output. And here is what that metrics pane will look like inside Otto. Pretty self-explanatory again, workflow metrics on top, node metrics on bottom. Again, pretty self-explanatory how these are measured. We just track the beginning and end time, number of failures, bytes processed, so on and so forth. And again, here's how it's stored in the database. Pretty self-explanatory once more. These are also relational to workflows. However, only one metrics entry at any given point is associated with a workflow. And this entry is created once a new workflow is created, and it's reset every time a workflow is activated to its initial state. This ensures that whenever you look at your metrics, that you can be assured they are current to what the workload looks like right now. And here's just, for instance, what the JSON B looks like for the average milliseconds to complete. Pretty self-explanatory again, various nodes and everything it would need to calculate that average. Yeah, and with that, that brings us to the end of our presentation. So if anybody has any questions, feel free to ask and we will get to them and do our best to answer. Let's see. Oh, we do have one question from Carl. Great job on the presentation, Otto team, and awesome looking product. Thank you. My question is about what factors informed your decision about where to position Otto on the low code, high code, no code axis, and how it impacted our approach in terms of allocating team resources. Yeah, that's a really great question. And that's something that we put a lot of effort into. And so deciding on our niche was definitely a challenge. We noticed that specifically in terms of ETL, that's something that there weren't as many solutions for. A lot of the low code solutions, for instance, were based around things like posting to social media or other things that were less, I don't know, less useful for larger tasks. And however, with the high code ones, a lot of them were very, they contained a lot of features and integrations and weren't really focused on any one thing. And that's something that we really wanted to emphasize, that we are a data-focused tool. In terms of the team allocation, basically we've rotated what we worked on. I don't know if anybody wants to go into more specifics on that. Anyone wants to take that one?
I can say something to that. I'd say we probably spent an even split to begin with. When we were working on our prototype, we spent an even split working on working on the front end and the back end. We deciding on initial architecture was relatively straightforward when we were putting together the prototype, and it evolved just a little bit from there. Later on, we spent a lot of time working on front-end things, working through React and managing state in regards to handling the flow of data through the workflow was something that took up a lot of our time. But yeah, I'd say we tried our best to make sure we didn't neglect any particular part of it.
And let me just jump back in. And one thing that I do want to mention on the back end, we spent a lot of time fine-tuning the workflow execution algorithm and making it more optimized. We ran into something fairly late in the game where we noticed a bug where certain nodes would start executing late. And we did run into that situation I mentioned before where we had nodes, or extract nodes specifically, extracting many, many times. And that turned out to be creating some of these issues. So we did spend quite a bit of time on that. And that's the bread and butter of our project, after all, is executing nodes. So that was definitely one of the more important parts of it. And we've got another question, and that would be, can each of you share a personal highlight or favorite moment from building Otto? Anybody wants to take that one first?
Yeah, I can start. I think what was particularly a highlight for me was when the user interface kind of came together. I spent a great deal of time building a UI, and I made a number of mock-ups in Figma, which helped to inform the UI. So it was nice to kind of transition from our prototype UI, which is very bare bones, into kind of a more polished final product. So that was quite satisfying for me.
Yeah, I can share next. So when we were building our app, you can see that we have different types of node and these different types of executions. And we kept in mind that we want to make our code modular so that when if we want to scale up and add more integrations, it should not be some major changes to the code base. So when we built our prototype, we kept that in mind. And at the prototype typing phase, we only have extract API. But because we did all the initial work to organize our code and make it modular, we were able to add Postgres and Mongo extract functionalities pretty much within one day, both front end and back end, and that felt pretty cool.
Yeah, let me go next. I think when we developed the second version of our execution algorithm, that was a high point for me. It was enjoyable kind of going through something that was a bit of a challenging code-related problem, how to manage the data in code. And executing it also in the midst of our, relatively complex system was enjoyable, writing out the code for it. So we all ended up contributing some to that because of the some of the bugs we ran into later too.
Yeah, and mine is kind of a higher level one, and actually it kind of feeds into the next question, which is we were a bit concerned from the beginning that our project might be a bit ambitious in terms of getting all of the moving parts together and the UI challenges. And personally, we actually managed to do that pretty quickly. Like, we had a prototype version in that we had a UI, it was basic, and it allowed us to transfer data and have a workflow running within a couple days. And that personally felt really good to pull that off. Just from there, we knew that we could flesh it out, but our basic functionality was there and we pulled it off ahead of schedule. That was personally pretty gratifying to me. Which feeds into the next question, which is, if another group were to attempt a similar project, what advice would you give them knowing what you know now? Anyone have any thoughts on that? I can jump in later.
Yeah, I have a couple thoughts. So this project had quite a robust UI and is definitely more product focused. So if a team was to build something similar, I'd suggest finding ways to outsource functionality as best you can. So I think that played a large role in our selection of React Flow. I think, you're just not going to have time to build everything from scratch. So it makes sense to focus on what's core to your application's functionality and really kind of hone in on that. And when possible, find other open source libraries that can kind of do some of the heavy lifting for some of the functionality. So as another example, in addition to React Flow, we also use Material UI to handle a bit of the styling, and it also provided several kind of React components that provided behavior out of the box. So that was big help for us for increasing our development speed.
And I was going to jump in on this as well. One thing that we did do, we could possibly have done even more of, we tracked our progress on the project in our to-dos in a GitHub project. And that was super helpful for knowing what needed to be done. One thing that I think that if we had more time, we would definitely have coalesced more is to have a really clear roadmap in terms of what features you would like to implement and what priorities they are, especially with the amount of time we have to build projects. One of the biggest challenges doesn't have to do with implementation at all, but simply knowing where to focus your efforts, just because there is so much that can possibly be done And also to, in your roadmap, ensure that you have a lot of different types of things that you can do, that they're not all the same kind of task, just bottlenecked at the end. And this can vary. I know in a professional environment that might not necessarily be the case, things might be more siloed, but on something like this, we do have the benefit of being able to expose ourselves to multiple different types of tasks and types of challenge. And so if people are doing a similar project, especially something like this, which is more of a product of an app, that's definitely something that's crucial, I would say. Awesome. We have another question here, which is that what was something that you found personally challenging about building it? Implementation challenges, for instance. Let's see. Yeah, we kind of mentioned part of that already with the algorithm. If anybody has something else along those lines. Yeah, I'd say that was probably the biggest challenge, was the core orchestration algorithm for us. So let's see, does anybody have any more questions? Now's the time. Here we go. What ideas do you have for future work? What features would you like to implement in the future?
Yeah, I can talk a little bit. Let me say a little bit something to that effect. So there are some things that we would love to be able to add to the app, such as additional integrations with other databases, so that it's a little easier for users to get access to their data and move it around as they'd like. We'd also love to increase capacity so that we can handle more than the 255 megabytes of data. Additionally, it would also be convenient to add some additional layers of abstraction so that users could more quickly pull apart and put back together their data. Some of the other tools out there have UIs that essentially allow you to grab bits of the data as if you're pulling it from like a bucket or something, and insert it into your code or insert it into a message or something like that. And having something to that effect could speed up the user experience. So
yeah. And we also, one other thing that we were kind of exploring toward the end was offering users different ways, different methods of extracting data from external databases. For instance, there's a type of extraction, called incremental extraction, where basically it optimizes how you would extract data from a database by allowing you to only extract what you need, especially if there's a very large database. And that's something we were looking into and definitely on our roadmap for the future. Oh, cool. We got another question here. How was it working as a remote team? I can take that one to begin with. We had a bit of an advantage here, which is that all of us are in close together time zones, Eastern or Central. So time-wise, that wasn't an issue. I know in remote teams that often is. In terms of how it was working, I thought it worked rather well. We had like Zoom meetings, or specifically Gather meetings. I'm not sure if you all are familiar with it, but I know Spot uses it. And we would concurrently work, and just being present in that way definitely helped get it done. Anybody else have thoughts on that?
yeah, I just reaffirmed that continuous meetings were very important. We had essentially 2 meetings a day, one in the morning and one in the afternoon or evening. And we did try to stay in the same space and gather so that we could essentially ask each other questions when they came up rather than having them take too long. There's always the concern that you don't want questions and help to get in the way of your own work. But in our case, when we were developing this app, we didn't run into too much of that, so we didn't have to worry too much.
And Gather is kind of nice for that, since there's a feature where you can quote unquote, if you need to really hunker down and focus on some code and not be bothered, like you can quote unquote go into another room and gather it. That will remove you from like any video voice calls so you can focus. And then if you need to consult with somebody, you go to their quote unquote office and do so. We made quite a lot of use of that. Cool. So if anybody else has anything they'd like to ask, we've got a couple minutes left, so now would be the time. Okay, so it looks like that's all of our questions. Thank you so much for listening to our presentation. We really like the app we built, and we hope it was inspirational to some of you in case you're interested in something similar.